My name is Jacob Torrey. I did this work also with Mark Bridgman, one of my colleagues who cannot be here today. This is actually about Crema, which is a much easier to remember title than the title in the program. Disclaimer, I do not speak for the government when I say this. I'm not part of the government, so just keep that in mind. So real quickly in a nutshell, so essentially what we did with Crema is we wanted to explore the sub-Turing space. So if you had an execution environment that you specifically limited when you created it, kind of rather than most programming languages that are kind of assumed to be Turing complete and then you kind of deal with the syntax, what could you do in these environments? And would that be able to reduce the risk of these weird machines? So if you could give the developers the programming tools to be able to do, say, a majority of their work, but make it just kind of by default more safe, and make these analysis problems easier, what would that look like, and what does this space look like? So the goal was we wanted to demonstrate that there was something useful in this space. If we got to the sub-Turing environment and we could only do the most trivial of computations, that might not be a very promising result. And so to do this, we created a programming language that targets LLVM, so you can embed it in existing software. And essentially, it won't let you write a program that is not provably halting using Walther recursion. And then we wanted to see what that space looked like. I went through and did some of my homework assignments from undergrad, my homework assignments, and then also explored existing code areas to see, how useful was this. And then the other part okay, now we have, say, this, we'll assume pretty useful space to play in. What does that do with either formal methods or program analysis? And so we found, empirically at least, or the future work would be to show this more formally, that you can annualize software with more granularity and then also at larger scale because you're spending less time on some of these hard problems. And then you have some analyses that might be undecidable when you bump into the halting problem or the undecidability cliff, that if you can kind of rescope your problem, they might now be possible to do some analysis. I don't think we need to talk about weird machines, but that's just there. LLVM, for those of you who don't know, Dan Geer mentioned is Keynote. It's an abstracted compilation tool chain. You basically generate assembly code for an abstracted intermediate representation, and then that can either be just-in-time compiled, it can be interpreted, or it can be compiled to native code for whatever target you're facing. One of the nice things about having things in this intermediate representation is that KLEE is a tool. There's a lot of other tools out there that can do static analysis or symbolic execution on this kind of abstracted language where you have a little bit more semantic information. So KLEE was designed basically to execute most or all of the code paths looking for crashes. And when the paper first came out, they were actually able to find some unknown bugs in BusyBox and some of the other kind of core GNU utils just because they never actually gotten that test coverage to those areas. So our problem is that I think the hypothesis was that full Turing complete languages, similar to that diagram of messages that we accept versus messages we want to accept, provides more expressionists than we think most programmers would need for a lot of tasks. And then this kind of gap in between where the program expressiveness that we want versus what we actually have is where these weird machines and exploits live. And so having more power than you need is kind of like having more rope to hang yourself with. So the majority of general purpose programming languages that we've seen out in the field are designed kind of with Turing completeness as, yep, we got that, we ticked that box, and now let's worry about some other things about memory safety or making it look pretty or make it really easy to parse. So that's kind of what everyone seems to do. And it's actually very, very easy to make something Turing complete. And so there's been some work from Sergey and one of his students showing that actually the memory management semantics of the x86 platform is in of itself Turing complete without actually executing any instructions. And then there's all the very small languages that might have 7 operands that can simulate any Turing machine. Once you get to that, then you run into also the halting problem. You kind of fall off that undecidability cliff, and now formal methods or program analysis becomes more difficult, and then also reference monitors kind of lose some of their power. So similar to the Lion King, you have a circle of life. In LangSec, we have the circle of bugs. So you start off with a complex data format, which requires a complex parser, which then is a hard analysis task. Then you have these undetected bugs or emergent properties from the weird machines. Then you have to put a NIDS in front of that, or a firewall or a FireEye type thing, which has some kind of underfit signature or overfit restrictions. And then to be able to kind of encapsulate those extra layer of defenses, you need a complex data format in your NIDS. And then it kind of goes around the circle until your turtle's all the way down. I don't think I need to say this to this group, but input parsing is safety critical. Basically, as Dan Geer said, that data is just attacker-controlled code that's being run on your system. It drives execution flow, and it allows, in many cases, arbitrary computation. Predicting the behavior of this is very, very difficult. And then that makes then software verification or validation is much more challenging. And so you run into this with the state explosion of trying to be able to find counterexamples, and problematically, you can't be able to kind of suss out all the bugs that may be in your software. So this is, Chomsky hierarchy, basically. So what did we do? So we developed an open source proof of concept language that specifically every program you write will terminate, which you can embed in other programs. So it targets LLVM, so you'd be able to write a C program. So say if you were writing a PDF reader, you'd be able to write the parsing routines itself that go from your input packets to your structured kind of typed data in something like Crema, because you never want to be able to parse something that will run forever. That would be very bad, to be parsing a PDF and never actually displaying it. And then you'd be able to pass that off once it's kind of in structured data form to a display or some other application that allows the user to interact with it without terminating after, say, 5 minutes. So this could be used as a parser bridge from the untrusted world into the formal type system. And so we're looking at these kind of bridges that we're able to kind of re-implement in Crema as either transducers or parsers that essentially convert kind of untrusted input into structured data, which is then input in a slightly more sanitized version to the main program body. We then explored this sub-Turing complete space kind of with a LangSec lens and seeing, is this something of value? Are there benefits from this? And some of the amazing, immediate benefits, your power is limited you're giving to the attacker because you're giving yourself less power. And so that right there is pretty intuitive. And then also we wanted to see how if you didn't have a halting problem, what are the weird machines like in that area? And finally, we wanted to look at program analysis improvements. So can we look at code more granularly? Can we look at larger amounts of code? Can we simplify the problems going to your SMT solver, saying KLEE to be able to kind of verify those constraints or paths? And we can make those easier so you can essentially touch more of your code. As we're generating code and now that machines are generating code, being able to verify that code becomes increasingly important. It was very scary to hear that machine-generated code already has vulnerabilities in it. So results, there's the link. I'll tweet that out. It's just at Jacob Torrey. But it's open source. Play with it, please. Submit pull requests, submit bug reports, anything like that. It's designed to be fairly easy to use, and it's capable of most with an asterisk programming tasks if you're thinking about it for this input-driven computation. There are some existing kind of sub-Turing languages out there that were written kind of from academic perspective, but they're not very intuitive. And so, coming back to the keynote, when you say you have some of these capabilities and compilers that are for experts, they're going to get either misused or they're not going to be able to be understood by the average day person who's moving a bit from one computer to another. So we wanted to make this as approachable as we could. And then also we took DJB's SMTP Qmail. And when he built that software, it's actually a very great model of secure programming. He actually kind of identified back many, many years ago that the parsing elements are the dangerous parts. And so actually that's a separate program. And so there's a separate process that does the parsing. And then he has a very, very simple kind of translation language between that process and the process that does the actual kind of mail work. And what we did is we took that and we ran that through KLEE. And then we also rewrote that same parser in Crema to see how we could compare. So that's what I'll get into in a little bit. So this is, fairly simple. The syntax, some of this stuff is going to get cleaned up, but it's fairly understandable right there. This is the Fizzbuzz, but I have more examples as well if people are interested later. So I'm not sure if this, yeah, you can see the graph. So if you look here, the number of paths to search in a kind of uncapped or unbounded, they grow much quicker and they're much higher than in the lower ones. So the red would be just kind of overall paths, and then the trimmed paths when you kind of can, tell the verifier or the analysis program that yes, this program will halt, and this is the maximum amount of state. What we did in the paper is we showed it as almost a just-in-time loop unrolling, and that you can kind of imagine an intuitive program where if you know the size of your input coming in, which is a requirement, or at least to be able to compute that in polynomial time, you'd be able to kind of create a forward-only execution environment that will then be able to, just by counting the number of branches, be able to kind of make a concrete understanding of how many states there are to search. And so you can kind of use this, and we talk about kind of a modified Turing machine in the paper, which is a little beyond the scope of this 25-minute talk, but how you can kind of work your way there from the other side to show that there's some trimmed paths that are much smaller and easier to solve. Looking here as a function of time, basically you'll see the red line is, we ran KLEE for a couple number of seconds and then stopped. And then these are the number of paths in the red line with the unrestricted that it had to be able to search, that it had queued up for the SMT solver to start looking at, versus the blue line, which is the number of restricted paths that it had queued up to solve. So KLEE, we actually got some weird results here, which I'll talk about in a moment, that essentially it starts by kind of finding all the paths, and then the ones that it finds interesting, it creates and passes it off to an SMT solver to kind of create a conversion from the symbolic constraints to a real-world example. And that's kind of where a lot of the processing time comes from. And so even though we didn't run the program for very, very long, it still had kind of a huge work queue for it to be doing, and much, much larger in the unrestricted state. Our instruction coverage as a function of time, also, if you only run KLEE for a very small amount of time, you get a slightly better instruction coverage. One thing to note about this is if you write the program Hello World and you run it in KLEE, you only get about 20% code coverage, just because printf has so many paths that you can't really explore if you don't put symbolic input into it. And so that's why you're kind of seeing this cap, and it's kind of running out, because there's just so many library functions that aren't going to be able to be explored unless you can specifically tell KLEE to start making those inputs as symbolic. But if you do that, then you start getting a much more increased time to suss out. So we wrote the Qmail parser, and then in the Crema parser, the instruction coverage was quite a bit higher, and the number of states that it had to explore was quite a bit higher in, so coverage was higher in Crema, states was higher in the C. The execution times are about the same because of that queuing. We pretty much just told it to run for about 30 seconds. So in that 30 seconds, what was happening here is that it had queued up quite a bit more to go to the SMT solver, which is why in the C version, it wasn't able to go and cover all those instructions. Whereas with Crema, since it had fewer states to go to in the beginning, it was able to actually complete a lot more of those right from the get-go. So Frank Schneider has a good definition of reference monitors, which are automatons that recognize a language of events. And currently they're prefix-based in the sense that they can only identify bad sequences of events, and then after that, kind of they have to say, all right, well, this prefix I know is bad, I'm going to stop that. So if you have a Walther recursive model, you can actually strengthen that to look at something beyond prefix only. You could actually look at an entire execution unit or computation, and you'd be able to determine on that because you know that your program is going to terminate at a certain point of time. And then if it is still running after that, you know that something has gone awry. And so with that, you can actually create much more stronger reference monitors. This is kind of analogous to your antivirus software running in kernel space, and it's very good against maybe your user space malware, but as soon as the malware gets into kernel space, it kind of loses that power. And so this is kind of an analogous jump where if your reference monitor has the full power and you're restricting what it's monitoring, you have some advantages there. So what we're trying to do, break the cycle of complexity, hopefully work towards verifying software out of the range for contemporary methods, limiting the risk through poor programming practices. So, in Crema, it's very difficult to write a program that would have some of these vulnerabilities in it, and then be able to provide some empirical data on these models. So what we want to do in the future, we want to look at, going and pushing it down even further. So LLVM, the intermediate representation, is kind of a full-powered environment. And so the attacker might still be able to inject intermediate representation code, which kind of can break out of this, expressiveness jail. So this could be done either as an FPGA or maybe a customizable CPU environment. So as I said, we kind of mentioned a CPU environment where you can enforce kind of forward-only execution of pre-loop enrolled programs. And then that would allow you to bring the Crema benefits to both hardware and embedded. We also look at more powerful formal methods tools. So, what might be possible now if you kind of have these assumptions for these restricted computation environments that before you kind of had to just assume were infeasible. This was one that Sergey came up with, looking at using some static analysis that at some point if the program gets too complicated or you see that this is something that is very safety critical, you might be able to tell the programmer, actually I would prefer if you rewrote this in something like Crema so we can actually analyze this a little bit better, which kind of is a sidestep around, obviously automatic conversion. So also in future work, is there some kind of heuristic automatic source conversion or at least ways to detect regions of code that could be done? So when NICTA did SCL4, they did a lot of this manually where they were kind of manually partitioning the Turing complete and the sub-Turing. Is there some tools that we could do to help that? And so that's some area of future work. And then obviously if there's some that are very obviously Turing complete, like an operating schedule loop or the Apache request loop, or there's some areas where maybe a human is needed to be able to make that determination. We want to be able to identify these input-driven codes, these transducers automatically, so that we'd be able to at least put bounds on what needs to be looked at. Hammer is a kind of parser generation tool and it also has kind of some built-in reference implementations of formal parsers. Is there some way that we could port some of that to Crema, and then that might get us some extra verification benefits? And then obviously for KLEE, one of the things that would really help if we could solve P equals NP, that would really reduce the time for SMT solving. So that's a good thesis project if anyone out there is looking for something. I'll be happy to put my name on that paper. So we wanted to look at programming language development from the bottom up of what tools do we need and how can we make a set that covers that, rather than here's all the power that our computers kind of replicate today as being kind of pseudo-Turing machines. Obviously, they don't have unlimited RAM, and eventually the sun is going to explode, so all programs will terminate currently. But something a little bit more tractable to analyze. So we're looking for that sweet spot. And we think that that's kind of, this reduced complexity is really the only safe method for input-driven programs. We wanted to look at these environments and then also looking at capabilities for formal methods and seeing how we could reduce the state space growth. So I'd like to thank DARPA for funding some of this work, and Dr. John Everett's back there. And then also thanks to some folks that helped with the ideas, Julian, Sergey, and Halvar. And with that, I think we can go to questions and discussion.
Let's thank our speaker. Hi, Sven Hallberg. One idea I had during your talk was, what if weird machines that we're worried about are sub-Turing, which I imagine lots of them might be, and so if we are looking at things from a LangSec perspective and saying, well, we want all our languages to be at the worst context-free and so on and so forth, we may be restricting our view a little with respect to the dark computation that Dan was talking about in his keynote. So do we just have to look out whether there is dark computation out there that is sub-Turing, and how do we find it? What's your take?
Yeah, so certainly, you know, a lot of those small bugs just come from memory computation. You know, just flipping a single bit or a byte would be the entire shell code, which is obviously, you know, that would terminate quite quickly. So I think, you know, getting to that point, this is a step in the right direction, and I think it allows us to hopefully kind of patch the dam into letting someone get to the point where they can get a weird machine and be able to control that weird machine, by reducing the kind of gap in between what we as a programmer are kind of intending for the program to do and what an attacker is able to get it to do. And so by reducing that kind of space, you know, clearly if there is still weird machines within that, and you as an attacker are able to get to that point, then you'll be able to still, you know, do your nefarious acts. But the goal, oh.
But you'd have a much easier time. You'd have a much easier time finding them when you're in the lower curve of analyzing code than on the upper curve. So basically, you know, yes, your needle can exist in any class of language, but you have a much smaller haystack.
Just one addition, maybe. So what I was mostly thinking of is just that we might want to remember that right now out there in the sea of dark computation that we have, there might actually be code that is sub-Turing and is still very dangerous.
Yeah, definitely. That's actually why we keep saying that Turing completeness is almost a distraction. Right? Because, of course, again, for the attacker, they are perfectly happy, you know, if there is a finite automaton that is drivable by your input, then the attacker will happily take advantage of that. But, of course, you know, the way what impresses people is root shell, right? And Turing completeness is really just the root shell of those machines, like hacking in the movies, you know. That's your VNC almost, even better than the root shell.
I wrote an article about this, about how kind of Turing completeness at this point is less of a practical measurement for what an attacker can do. I mean, you can be playing, you know, the example of the language that is kind of inappropriate to say, but starts with a brain and ends with an F and then a bad word. That is Turing complete. However, if you are able to break into that environment, all it can really do is increment a couple integers and simulate that. Whereas if you can write to arbitrary memory or send packets, that's a much more powerful thing, even though it might be restricted. So I think they're actually orthogonal to the sense that you know, what you can do and your capabilities to be able to, say, impact systems from afar is what your goal is as an attacker. And it's not necessarily to be able to run the most complex computations. And so I can talk to you offline about that, but I think this is, as Sergey said, it makes the haystack smaller to search for, but you're still going to have these very poignant attacks in this small space.
More questions?
So one comment you had was that maybe, you know, sort of static analysis and formal tools could do better if they had a restricted programming language. And well, I just wanted to add a comment there that that's kind of what they've been doing for a long time, like starting with the early development of model checking was, let's assume finite state programs. And then when they did the SLAM project at Microsoft, they also had like Boolean programs where you only had Boolean data type, right? So So in a sense, I guess KLEE is pretty recent, but historically we already had and analyzed programs in restricted languages because it would have been undecidable otherwise. And I guess the only difference would be whether you need to abstract or not, like whether the results are approximate or not would change. Do you see what I mean?
Yes, I think this is kind of bridging the gap of, you know, we've built up a lot of tools already there, and now it's just a kind of a matter of combining them to be able to make tools analyze real source code, so to speak, with all these kind of things. And that's kind of where we're looking down the road, is to be able to kind of, you know, bridge that gap and apply a lot of the tools that have, you know, come out from the more simple verification tasks to a quote-unquote real programming language that you'd be able to at least write a portion of your code in.
It's funny how model checking is not entirely present in the parsers, in the practical parser space. And so I was talking to various people about software verification, right? And somehow parsers, even though to an attacker, this is the closest and the most valuable piece of code, for some reason they have not been as much of a target of program verification as we would like them to be. And so it's say, for example, to an extent, this has to do with the loopy nature of parsers. So Holler Flake had a challenge problem for static analysis, which consisted of a very simple loop in the sendmail and an actual bug that was found there. And Julien has done work with that challenge. But basically, I mean, it was a 5-state loop of consuming single characters that presented a problem. So what made this approachable was semantic annotation of what is meant to be done here. But as a piece of C code, even that kind of a simple bug was you know, enough to be a challenge that stood for a year.
So one remark about that. One thing that was not addressed in this talk, and we haven't talked about quite yet, is the fact that it doesn't really matter how complex the code looks like, but what matters is how contextual the implementation is. Because the more contextual a certain, you know, say, language will be, or like a property will be, then the hardest is going to be to try to prove this property with tools such as SMT solvers, which are otherwise really easy to use and can capture simple finite state machines like symbolic model checking would do. So I don't necessarily think that model checking is a bad technique or SMT solving is a bad technique, but for some classes of properties where you have a huge amount of context, or the context is deep, then that's where it would usually be hard to prove the properties. So maybe that's things we should research more.
So, I mean, I would slightly disagree on the... So I think we know how to handle the loops and the recursion, actually. So if you give me just programs with Boolean data type and arbitrary recursion, we can analyze them. Like, there are tools you can download that'll analyze that. And I think the issue with parsers is really strings. Like, strings as a data type are not... Like, it's very hard to reason about. We don't have good SMT solvers for them. Like, it's very early stage. And to the extent that we can, we do C strings, but we treat them as bit vectors, right? And that's the only reason we can. So I'll agree with you that the tools are not there. I'm just disagreeing on the reason why the tools are not there.
They would seem to require significant adaptation to where we want them to
Yes,
be.
absolutely, absolutely.
Security. Because again, I don't think it would be hard to make a quantitative point that if you were able to verify parsers, you'd get rid of a bunch of CWEs and an even bigger bunch of CVs, right? The payoff here is quite obvious. So we see a bit of impedance then between verification, where it's primed to produce those results for practical security, and the reality. Well, people verify things starting with abstract syntax trees. So why is that, right?
It's Falcon here from Leviathan Security. I was thinking about this, and I was thinking that perhaps you could compose a bunch of these machines written in Crema together that are Turing incomplete and create a Turing complete machine. And I was kind of wondering two parts from this. One, is my hunch true that these can be composed if they're composed dynamically? Does that in any way take away from the usefulness of formally verifying these systems? And the second part, if it doesn't, could you then model something that must be Turing complete, like for example the Apache event loop that you were describing before, as simply a dynamic concatenation of these machines and thereby secure it?
Wow. Yeah. So one example to look at that is the Linux real-time fork, which is basically a real-time version of the Linux kernel. And that has your kind of fast loop, and then it kind of farms out to these things that have strict deadlines. And they're not necessarily sub-Turing complete. They just kind of get halted if they misbehave. And so with that, you can kind of look at the Linux kernel's execution as a concatenation of these small tasks that are basically coerced to be provably halting, in the sense that once their time runs out, they're killed. As about composition, I think it really depends on what you're looking at. So again, that's what we're talking about is, if you look at something where you have composition of multiple, say, layers, where you have your Crema program running on your, larger LLVM, and then you have your assembly with all the pipelining, which, as I said earlier, is the new high-level language. If you're composing in that space, then certainly, there might be some interesting interplays between being able to trigger something in a different part. You'll have to look at, what we've done in terms of, the compile time, syntax checking, and kind of restrictions to see. And so if you're looking at Walther recursion, which is kind of the space, it's been shown pretty much whether our current research prototype reflects this perfectly or whether there may be bugs is a different question. But that's been shown pretty much that composing Walther recursion algorithms will still be able to be determined in polynomial time, the termination bounds.
Is this like sequential composition, like piping them together? Or, I guess one question I have is, is mutual recursion legal in Crema?
So in our current implementation, co-recursion is not permitted. Mm-hmm. We're looking at using continuations as a way to kind of boundarize between regions of code that may need more power, or at least be able to kind of logically isolate. But the research prototype we have does not include that currently. It's more restrictive than what it probably at some point could support.
Anything else?